This next question is from Unit 4, June 2018, question 2. It's a sort of a combination of gravitational fields, electric fields, and also a little bit of sort of kinetic theory in here as well. The first part of the question is all to do with the derivation of a formula for escape velocity. What we've got is half mv squared, which represents the kinetic energy of an object, and minus gmm over r, which represents the potential energy of an object, both of these objects having mass m, or just one object in fact. What we've got to do is realise that if we get an object to escape from the Earth's gravitational field, it's got to reach infinity, where its potential energy would be zero. And we're also going to just give it enough kinetic energy so that when it reaches infinity, its kinetic energy will be zero. So at infinity, its total energy must be zero. And therefore, from the law of conservation of energy, the total energy must be zero on the surface of the Earth as well. So what we've got here is the expression gives us the total energy of the object, and that's got to be equal to zero. And then when we take this object to infinity to get it out of the Earth's gravitational field, then its total energy will also be zero at infinity. And hence this equation is just showing conservation of energy. Next, we've simply got to use that expression to calculate the escape velocity from the Sun given the mass of the Sun and the radius of the Sun. So let's first of all rearrange the equation to half mv squared equals plus gmm over r, moving the minus gmm over r to the other side makes it positive. The mass of the object escaping cancels out, and then we'll be left with v being the square root of 2 gm over r. So if we substitute in some values, 2 times 6.67 times 10 to the minus 11 times the mass of the Sun, 1.99 times 10 to the 30, over the radius of the Sun, 6.96 times 10 to the 8 meters. If we substitute those values into a calculator, you'll get 618,000 or 618 kilometers per second, 618,000 meters per second. Next, we're told that the surface temperature of the Sun is 5,780 Kelvin, and we've got to use a kinetic theory equation to show that the RMS speeds of a free electron on the surface of the Sun is approximately 500 kilometers per second. Well, one of the formulas that we have in the data book is that U equals 3 over 2 nkt, where U is the total translational kinetic energy of all of the molecules there. If we divide both sides of that equation by capital N, the number of molecules, we're left with the kinetic energy of one molecule on the left hand side and 3 over 2 kT on the right hand side. We're trying to find the square root of the mean square speed. So what we're going to do here is simply say that the mean square speed, the 2's can cancel, is 3 kT over m, and the RMS speed will be the square root of 3 kT over m. Substituting values in. Boltzmann constant 1.38 times 10 to the minus 23. Temperature 5780 Kelvin. And for the mass here, it's the mass of the electron given in the data books as 9.11 times 10 to the minus 31 kilograms. Substituting those values in will give us that the RMS speed is about 513 kilometers per second. Next, by considering those previous answers, we need to explain why the Sun has a slight positive charge. Well, at first thought, or first glance, it looks as if the speed of the molecules isn't enough to actually escape from the Sun. But remember that the RMS speed is just an average speed of all the molecules, and many more molecules will have speeds greater than that and are able to escape because of the way that the molecules continually pass energy between each other in collisions. So let's talk about some electrons gain enough energy in collisions to reach the escape velocity. Quite clearly then, if we've lost some electrons, that's going to make the remaining sun positive because the electrons are negative. But the main point we're looking for here is that some electrons are moving fast enough, and that's because of the random collisions with other molecules. Next, the student claims that a small positive charge of approximately 0.08 coulombs on the Sun is enough to produce an electrostatic force equal to the gravitational force on an escaping electron. We're going to determine whether or not she's correct. So let's first of all calculate the gravitational force using gm1m2 over r squared, 6.67 times 10 to the minus 11, times the mass of the Sun, 1.99 times 10 to the 30, times the mass of the electron, 9.11 times 10 to the minus 31, over the radius of the Sun, which I just need to check again, 6.96 times 10 to the 8. And its radius squared. So if we plug those numbers into a calculator, we'll get that gravitational force is about 2.5 times 10 to the minus 29 newtons. Next, let's calculate the electric force given by 1 over 4 pi epsilon naught, Q1, Q2 over r squared. 1 over epsilon naught, 1 over 4 pi epsilon naught rather, is 9 times 10 to the 9. The charge of the Sun is the 0.08 coulombs. The charge of an electron is 1.6 times 10 to minus 19 coulombs. And again we have the 6.96 times 10 to the 8 meters radius of the Sun squared. And that gives us an electric force of about 2.4 times 10 to the minus 25 newtons. So because those two forces are very similar, we can conclude that the student is probably correct. Not quite, but close enough. For the last part of the question, we've got to estimate the percentage of lost electrons compared with the total number of electrons on the Sun. And we're assuming that the Sun is mainly hydrogen and that it's lost a 0.08 coulombs of charge in the form of electrons. So first of all, let's work out the number of electrons in that 0.08 coulombs of charge. So simply 0.08 divided by the charge of one electron. And if we put those again into the calculator, we end up with 5 times 10 to the 17 electrons. So those are the number of electrons that have escaped. If we want to estimate the total number of electrons that the Sun was made of, well, we just remember that a hydrogen atom is simply a proton plus one electron. So if we can work out how many protons make up the mass of the Sun, then we've also got the number of electrons. So to find the number of protons on the Sun, what we're going to do here is take the mass of the Sun, the 1.99 times 10 to the 30 kilograms, and we're going to divide it by the mass of a proton, which is near enough 1.66 times 10 to the minus 27 kilograms, maybe closer to 1.67, simply because the proton is a little bit more than one unified atomic mass unit in mass. That will give us about 1.2 times 10 to the 57. So if we're trying to find the percentage of lost electrons, we're going to take the actual number of lost electrons divided by the number of electrons that the Sun has and multiply it by 100 to turn that into a percentage, and that's going to give us something like 10 to the minus 38%. Thank you for listening.